He's played with some amazing people throughout the world, some of the best in business. And I had the wonderful chance to meet him this last summer. So anyway, he said he would love to come and talk to you about a program that he's developed, and I'll let him share more of that with you. It's called Music Mechanics. I was so interested in it since I knew he'd be teaching at Biola. And so today, welcome Mr. David Enos.
Thank you. Anyway, I have a YouTube channel called Music Mechanics, and before I continue, I wanted to thank you, Noel, so much for the kind, gracious invitation, and I appreciate your friendship. And
It's a blessing.
yes. So this lecture will be related to my Music Mechanics series on YouTube. Hopefully, it'll be entertaining and educational. Please feel free to ask questions, and just so you know, after I finish a subject, I will stop and ask you also if you have any questions. So, why don't we begin by show of hands? How many singers are in the audience? Okay, good. Instrumentalists? Okay. Improvisers? All right, all right. Audio engineers? Okay. Okay. Songwriters. Excellent, excellent. Composers. Okay, good, good. I happen to be all of these. I actually started as a heavy metal vocalist. It's okay to laugh, guys. Then I became a jazz bassist, an audio engineer. Is one of the things that I do. This is on location. And I also do engineering for like video game trailers and stuff like that. I did all the arrangements for Dick Van Dyke for his last album here that came out. I take it you know Dick Van Dyke? Okay. And I also did some studio work. This was for the Olympics some time ago for CBS News, and that's me doing other studio work with a bunch of strings and some touring and like that. So why do I bring this up? Because for me, all of these varied experiences are usually tied together in a way that helps me understand how music is put together. And if you're open to receiving everything from all sorts of disciplines, you can learn a lot. Basically, everything that I ask you has something to do with music theory. That's kind of where I'm going with this. And so that's what music theory is. It's a way of trying to explain and understand music. I've always had an insatiable curiosity about how music is put together, the mechanics, if you will, on how all the parts work synchronistically, which is why I've actually named the talk Music Mechanics. Perhaps this is how you feel about music theory. It's really not that bad. In fact, once you get your head around it, it's a blast. But to understand it, you must have a rock-solid foundation in the basics. Much like, if you were studying to learn calculus, you'd probably start with what? Addition and subtraction, multiplication, right? Division. Then you'd move on to algebra, perhaps. Geometry, then trig, then calculus. There's kind of an order of the way to do things. So something that's similar is in the music industry, our rudiments are intervals and scales and chords. This is the basic building blocks, the foundation, if you will, on music theory. So in understanding how music works. So you also find that music is a language, and the different genres of music are similar to different accents around the world. I mean, we're still using the same 12 notes, aren't we? But you may go to New Orleans, you'll hear one kind of music. You go to LA, you hear another kind of music. And it's kind of like the different accents that you get. There's a New Orleans accent, there's a New York accent, there's a Los Angeles accent. So every style has its own sort of accent. Even though we're speaking English, we all have an accent from different genres or different regions, if you will. So it's kind of the same concept. We're still using the same 12 notes, but which 12 we use in any particular style is going to determine what we choose. So certain things are appropriate, certain things aren't. That's kind of the gist of it. You might play this in a certain style, and another style you're not going to play that at all. You might play something else. So to get started, let me show you one way that these different but related disciplines I've learned can work to understand the whole. We'll begin with audio. So this is a waveform. This is a graphical representation of a recorded sound in Pro Tools. In this case, it's a sine wave, which is a simple single frequency. We'll discuss what frequency is in a minute. This is kind of along the lines of the physics in music. This is the sound audio side of things, but there's a point to this. So this waveform is made up of many wavelengths, and this is a wavelength. You see the point from crest to crest? That's a wavelength. That means you've completed one cycle. The size, like if you go here, the crest simply means the top of the compression phase. The trough means the bottom of the rarefaction phase. So what is compression and rarefaction? Well, if I clap like that, what's happening is I'm initiating a sound. There's energy coming here. And you've got this compressed air. Basically, the air between me and you is compressing. And then, so that's the compression phase. And then it's expanding and compressing and expanding until it finally reaches your ears. That's how sound works. And your ears pick up on that. And it interprets it into frequencies. What amplitude is simply volume. If I record something and it's softer, what this wavelength is going to be a lot shallower. And this right here is just called the zero crossing. This is where you have silence. So frequency is a measurement of how many wavelengths, how many of these wavelengths right here, from crest to crest, or it can be from trough to trough, or it can be from 0 point crossing to 0 point crossing. What you're looking for is one complete cycle. Does that make sense? That's where the term cycles per second comes from frequency. Frequency means how frequent do those wavelengths pass by in a given second. That's all it is. So it's a measurement of how many wavelengths occur per second and is measured in hertz. And if it's really high, it's measured in kilohertz. So the more frequent the wavelengths occur per second, the higher the pitch. Which pitch means the highness or the lowness of the sound. You know, this is high pitch, that's low pitch. So the less frequent, of course, is the opposite. The less frequent the wavelengths occur per second, the lower the pitch. So does that make sense? Okay, good. So let me actually demonstrate this. What I'm going to do here is I'm going to play a sine wave in different octaves. And I want you to notice this because this is really actually kind of fascinating. So this is a sine wave at 440 hertz. It's a simple single frequency, and you can see the hertz right here. I've named it right here. So that's 440 hertz. So if I spread this out, this is an actual, me actually recording a sine wave in Pro Tools. So I'm going to spread this out. Actually, first I'm going to show you, that's 880, sorry. Yeah. So we started with 440, that's 880. Can anyone tell me what the difference, what that interval is from the low one to the high one? It's an octave. That's right. Here's the interesting thing. An octave, we all know, does everybody know what an octave is, right? Okay. An octave is actually divisible in half or double. So there's an actual physical, natural reason. There's an order to the universe. There's a natural order to this. If I have 880 hertz, that's twice 440. That's an exact octave. What do you think is going to happen if I half this? What's half of 440? Anybody? 220. You think I'll get an octave down? Remember I said we're looking for wavelengths, right? There's one wavelength right here. one wavelength at 440 occurs for two wavelengths at 880. Does that make sense? And now I'm going to add another 220, and we'll find out if it's an octave lower than the 440. Let's see. Sure enough, there it is. Now, what do you think is going to happen? This is two wavelengths to one full wavelength here at 220. One full wavelength at 220 equals two full wavelengths at 440, which equals 4 at 880. So all these R's are octaves, divided, right? As the frequency gets higher, right? Or if you double the frequency, it's an octave. If you half the frequency, it's an octave lower. Everybody understand so far? So, this is why things sound higher or lower. Each frequency is found at a specific pitch, which is also assigned a specific note name and location on a music staff. So there's all your instruments and voices. Are voices in there? Yes, they are. And each one of these frequencies is assigned a specific note name. If you look down here, this tells you what the frequencies are. It's kind of fascinating. Engineers can use this quite a bit because it'll tell you, a lot of times if you're mixing for, let's say, a large orchestra, which you may do with sample libraries, you're going to get a lot of clutter and a lot of stuff that you don't need. So what you do is you look at something like the double bass. These are the frequencies that it produces. So you let down and find out, okay, well, what is this, 41.2? Anything below 41.2 I can get rid of. You can clean up the low end, or you can clean up the high end in the same way. So,
what is this chart called again?
what is the what?
What is this chart called?
What is a chart, Carla? That's a, I don't know what I typed in. I think I typed in instrument, ranges, frequency. Probably something like that is probably get you in the ballpark, I would imagine. Yeah. Kind of interesting, isn't it? When you see the actual notes translated into frequencies. So, but a sine wave or single frequency doesn't exist by itself in the real world. It's only created with synthesizers. In truth, any instrument or piano or voice produces a single note. Producing a single note, like if I play this note, it sounds like a single note. It's actually not. It's producing several frequencies at the same time. We only hear the loudest frequency, which is called the fundamental. Whenever you play a single note, you may hear one note, but there are actually other frequencies happening at the same time, but at softer volumes. This is called the harmonic series, and any frequencies in the harmonic series other than the fundamental are called partials. These vibrations are happening simultaneously. So to prove this, this is actually really cool. Here's a little video, and what this guy did was take a strobe light. He vibrated a string. The video starts out with him vibrating the string. And then he sets it. I think it's set up with a speaker, if I'm not mistaken. I think from the looks of it, it looks like a speaker cone or something that the string's sitting on, and he's feeding it an electrical impulse. And what's happening is, as it's being tuned to a certain frequency, you see the strings start doing this, right? And then as he doubles that frequency, you'll start seeing it do the typical wavelength kind of thing. So check this out. This is really, really cool.
So we can see this physical representation of the frequency. And there'll be a certain point where the wave, the string will respond. Look at that. Now. So we're finding a point where the outgoing wave and the reflected wave build on each other to create large crests, large troughs. So that's a standing wave. This is the first order, it's called. This is actually half of a wavelength. If I double the frequency, we'll see what we get. 8.8. Okay. All right, so we'll go a little less
Watch
than
what happens
18.
here.
And this is one full wavelength now.
So this is actually cool because what he's actually doing in the next thing is he keeps the frequency the same, but he puts a strobe light on it. And remember the harmonic series, right? You've got this 1, and then you've got, it's divided in 2, and then 3 and 4. He uses a strobe light at a specific timing. And what happens is, even though he hasn't changed anything in the string's vibrating the same way, as he changes the frequency of the strobe light, you start seeing those other partials. It actually is in sync with the other partials. Check this out. This is amazing.
And this is one full wavelength now.
So here's the original.
Dial in the frequency.
Oh!
And there we go.
You can even see it go slow on the edge. Oh, that's so cool.
Wait, so what is happening right now?
The frequency of the strobe is equal to the frequency of the string. So
that's when it stays still.
yeah.
Okay.
How cool is that? So as you can see, every time I play a single note, like this G down here, all you're hearing is that lower partial, the fundamental. You're not hearing all the partials on it. You're only hearing the fundamental frequency. There are other frequencies sounding at the same time, just to a much larger or lesser extent. The harmonic series of a single note can be translated into musical notation. So for example, if I play this low G, what's playing along with it would be this, and so forth and so on. Do you happen to notice how the intervals here, this is what I want you to focus on. Notice how the intervals here are getting tighter and tighter and tighter. More compacted up here, aren't they? What's going on down here? They're opening up, aren't they? When you play one note, the series is spread out more at the bottom and tighter at the top. Does everybody understand that? Okay. This is where it starts getting into actual music. You ever notice how I can take a chord, like any chord, let's take like the worst chord possible, like a polychord, a B major chord over or a C major chord over a B. So I've got this. Here's my C major triad, and I've got a B major triad. Right? Sounds awful, right? But what if I spread that out? What if I take the same notes works. Why does it work? Because I'm taking account, and you may not know this, you may know this instinctually, but maybe you didn't know why. A lot of times you play chords on a piano, and if you play them too tight, which is called closed position, if you play a closed position chord down really low, it sounds kind of muddy. If you open it up, or if you play that same chord up higher, in the higher register, it sounds just fine. Move it to the lower register, it's awful. So we're just kind of going along with the physics of what's happening here. We're actually taking into account the physics and the harmonic series. Does that make sense? What you're doing is you're reinforcing the harmonic series. It's more spread out in the low range, more compact in the upper range. And just so you know, this isn't just my opinion, the famous Russian composer Rimsky-Korsakov wrote a book called Principles of Orchestration. And he even talked about this. If you look here, this is on page 67. It says the normal order of sounds or the natural harmonic scale. What he's actually talking about is the harmonic series. What we just talked about, the fundamental, the partial, all that. This is the same thing. This just happens to be in the key of C. We got an octave, then a fifth, and then a fourth from there, and then third. This actually mirrors what I just showed you, except in C rather than G. It's the exact same thing. The normal order of sounds, or the natural harmonic scale, is what he calls it, may serve as a guide to the orchestral or arrangement of chords. It will be seen that the widely spaced intervals lie in the lower part of the scale, gradually becoming closer as the upper register is approached. And if you look at this voicing, I mean, this is kind of mirroring what's going on here, isn't it? So the next time you sit down at the piano or you play guitar, think about why that is. You know, you're playing a chord and it's kind of spread out in the left hand on the piano, and it happens to be a little tighter on the right hand. This is why. Does that make sense? Any questions? No? Wow. Congratulations, you just learned about music physics. Not so bad, was it? Question?
So you're saying it's more spread out in the left hand because we need the lower frequencies to be more spread out because they're more.
That's correct. That's correct. The lower the frequency, even if you're arranging, let's suppose you're arranging for a brass choir. If you're arranging for a brass choir, if you don't want it to sound muddy, you don't want like a major triad like this. That's not going to translate well. So I might take this third here, flip it up an octave. Same chord, I just changed the voicing. Does that make sense? So the lower it is, the more open voicing you need. The higher it is, the more closed. You don't have to be, like you can still play, you know, like that. You can still do that up high. I'm just saying that as far as the lower frequencies, following the harmonic series will keep you out of trouble. Meaning, the lower you go, the wider the voicing. Does that make sense? Okay. This is an example of how understanding of sound and audio can reinforce your understanding of music theory, chord voicings, and orchestration. So this is my audio side of me helping my musician side of me. Hey, thanks for watching the video. Be sure to like and leave a comment below if you have any questions. And don't forget to hit the subscribe button